In this video, I want to take a look at two theorems which tell us when we can expect to find solutions to differential equations, first-order differential equations, and how many solutions we would expect to find. So here we go. First one is going to be just for first-order linear differential equations, and then we'll do the general first-order equation afterwards. So here we go. Suppose P and G are two functions that are continuous on an open interval I. Right? So that is the set of values of t that are somewhere between alpha and beta, but not including alpha and beta. Okay. So that's my open interval I. And that open interval contains the point t0, which now looks a little prettier. T0 is going to be the t value of my initial condition. So I want to make sure that these functions p and g are continuous on an open interval containing that value of t. Okay. And if we have that, then there exists a unique function, unique meaning only one, y equals f of t, that satisfies the equation y double prime plus p of t times y equals g of t. This is our first order linear differential equation. For each t in that interval. So the solution that we find is both defined and continuous in that interval where p and g were both continuous, and that this also satisfies the initial condition y of t0 is y0 for any arbitrarily chosen y0. To prove this theorem, we mainly have to look at the method that we have for solving first order linear. When you think about what we do, we take that equation, we look at p of t, and then we find an integrating factor, which is e to the integral of p of t dt. Now, when you integrate a function, as long as it's continuous, it does have an antiderivative, and the antiderivative will be continuous on the same interval that it is. And so then if you do e to that, well, the exponential function is continuous everywhere. So the discontinuities of this integrating factor are going to be completely determined by the discontinuities of p. So wherever p is continuous, so will this integrating factor. Okay. And more so, that integrating factor is never equal to 0. Because no matter what this function p of t is, when you integrate it, you get some other function. But e raised to any power, positive, negative, or 0, it will be a positive number. E to a power is positive. So this is never 0. Now, on the other side of the equation, as you're solving this first order linear equation, right, you multiply both sides by that integrating factor. Now, when you integrate this right-hand side, it'll be g times this integrating factor. That the product of two continuous functions is continuous. So if you're in an interval where both p and g are continuous, then the product will be continuous. And so will the product with this thing be continuous, because we've already mentioned that this is continuous whenever p is. So that big thing inside that integral there is a continuous function as long as p and g are. And when you integrate that, that will also be continuous in that region. So, so there's no problems there. Then the last step of solving for y is you got to divide both sides by the integrating factor. Well, we've already noticed that that integrating factor is never equal to 0. So when you divide by it, you don't introduce any new discontinuities, right? Because the quotient of two continuous functions is still continuous, provided that you're not dividing by 0. And we're not dividing by 0. So the solution that we have of y equals 1 over the integrating factor times this integral is continuous whenever p and g are. All right. Now, how do we know that there's only one solution? Now, I have to admit that the book gives a reason which is kind of like when you plug in your initial condition and you solve for c, you only get one c, right? There's only one. There's just a plus c that comes on in the end, and it's a linear in c, and so you only get one solution for c. Well, okay, but who's to say there isn't another method of finding a solution that might give something else? So, yeah, they give an argument, but it's within the context of the way we solved it. It doesn't preclude other solution methods and maybe other solutions, but this is a special case of a more general theorem that we're about to look at. So, and that also has a uniqueness to it. Okay. So anyway, first order linear is kind of nice. If you know, you can look right at the equation. You can say, hey, I know where P is continuous, I know where G is continuous, so you know where both of them are continuous. And then you can say, okay, so my solution will be continuous in that same interval. Now, for the general first order linear equations, we have the following theorem. Let me move myself out of the way here. So suppose you've got a function of two variables, t and y, and the partial derivative of f with respect to y. Suppose that those are both continuous on some rectangle where t is between alpha and beta and y is between gamma and delta. So in the ty plane, you're describing a rectangle, okay? And in that rectangle, you know that both of these functions are continuous. Now, if you haven't had Calc 3 yet, you might not have dealt with partial derivatives and you don't quite know what that means. Let me just say that partial derivatives are really pretty easy if you know how to take derivatives, because partial derivatives are just, so you are just derivatives, but you let all the other variables be a constant. So for instance, I'm describing f here as a function of both t and y, but I'm taking the partial derivative with respect to y. So I would just treat t as a constant and just think of it as a function of one variable, y, and go from there. So partial derivatives are pretty simple. So here we are, we've got this rectangle in the ty plane, and containing that interval's got to contain the point t0, y0. So t0, y0 is going to be our initial condition, and we've got this rectangle around it. And we know that in that rectangle, this function f and the partial of f with respect to y are continuous. Okay. Now, the conclusion is then in some interval where t is between t0 minus h and t0 plus h. Now, we had a bigger rectangle here, and I'm maybe describing a smaller interval now, right? But this has to be between alpha and beta. There, that looks better. Then there exists a unique solution, y equals phi of t, to the initial value problem, dy dt equals f of t and y of t0 is y0, okay? So let me rephrase this or state it again. You're looking at just a general first order differential equation with an initial condition. We're saying my initial condition's here. I've got a rectangle around it where I know this function f is continuous and I know its partial with respect to y is continuous. Then I know that there is a solution that passes through my initial condition. Now the interval on which that solution is continuous is from some t0 minus h to t0 plus h, and which may be smaller than alpha to beta, but so it's still in there. And I know I have a solution, and I know it is a unique solution. It says right here, there exists a unique solution, only one. Okay, so notice, for instance, that this, if I compare this to the first order linear is a first order differential equation, so this should apply. So if I take that first order linear equation and solve it for y prime, then this function right here, g of t minus p of t times y, this is the function f of t and y. This is a function both of t and y. It is linear in y, and so it's continuous for all y. And it will be continuous in the t direction as long as p and g are. So, and also the partial derivative of this thing with respect to y, partial derivative with respect to y, remember I'm thinking of t as a constant, so g of t would be a constant, and p of t would be a constant. So you're looking at like 3 minus 7y, and the derivative would be whatever the coefficient is in front of the y. So the partial derivative of f with respect to y is just minus p of t. So this function is continuous in the rectangle. I have a picture down here I'm just saying, supposing P and G have vertical asymptotes or something, some sort of discontinuity at -2 and 4. And so there's this interval here from -2 to 4 where they're continuous, but then y is continuous anywhere, so y can go all the way up and down. So the rectangle that we'd be talking about, this rectangle that they talked about up here, would say alpha and beta are between -2 and 4, and beta and, sorry, gamma and delta would be -infinity to +infinity. Right? That would be if my initial condition was in this region. But if the initial condition was out here, then I might be saying, oh, alpha and beta are from 4 to infinity, and again, y would be from -infinity to +infinity. Or if my initial condition was over there somewhere, then the alpha and beta would be from -infinity up to -2, and y would be from -infinity to +infinity. So the thing is, the discontinuities in P and G cut the t-axis perhaps into some intervals, and then depending on where your initial conditions are, that would determine which part of the plane we're talking about that keeps both P and G continuous, because it doesn't matter what y is, that's always going to be continuous. Okay. So in the first order linear case, you've got these big tall rectangles that are only determined, they're discontinuities, they're determined by discontinuities of P and G. Okay. The proof of this general theorem will be discussed in section 2.8, and we will get to that next week, I think. Anyway, let's just do one quick example to see what some of those rectangles might look in a different situation. So here's a differential equation, dy dt equals t times y all raised to the 1/3 power. Okay. Now, multiplying t and y together, t by itself is continuous, y by itself is continuous for all t, for all y. And so you multiply those together, that's continuous in the whole plane. Taking the cubed root, yeah, it doesn't matter, positive, negative, 0, you can take a cubed root, that's continuous everywhere. So this function is continuous everywhere. But the partial with respect to y now, think of t as a constant, the partial with respect to y looks like this. The t to the 1/3 is just a constant, and then the y to the 1/3, you'd have 1/3 y to the -2/3, so it looks like this. And this is definitely not continuous everywhere, because at y equals 0, you got an issue. So on the x-axis, this is not continuous. So if your initial condition had a y0 which was positive, then the rectangle you'd be talking about would be t from -infinity to +infinity, and y from 0 to infinity. So that top half of the plane would be good. If, on the other hand, your initial condition had a y0 which was negative, then the rectangle you'd be talking about is down below. It's just, you can't include the y-axis. All right. The book gives an example very much like this one. Instead of t times y to the 1/3, they just talk about y to the 1/3. And they show how they can get multiple solutions all passing through the same point, which seems odd because the uniqueness theorem says there's only one solution. However, the y value of the initial condition is y equals 0, which is on a spot where this function is not continuous. No, the function is continuous, but the partial derivative is not continuous. And so the theorem doesn't even apply. It says if we have those conditions, then we get a unique solution. But if you don't have those conditions, maybe you do, maybe you don't get unique solutions. And in the example they give, they certainly have more than one solution. Okay. So we will look at this in more depth in the next video.